When you really strip a camera down to its essence, it stops being a magical object and starts looking more like an intricate collaboration between physics, chemistry, and engineering. But the deeper you go, the more impressive it becomes, because every single part inside a camera exists to solve one very specific problem. How do you capture light, control it, translate it, and store it without losing the moment it represents? Let's open the camera up, not physically, but conceptually, and walk through how it's actually built. At the very front sits the lens system, and this is far more complex than just a piece of glass. A modern camera lens is made up of multiple glass elements, each precisely shaped and layered. These elements are often made from specialized optical glass with coatings designed to reduce reflections, improve contrast, and correct distortions. Inside a lens, you'll find groups of these elements that move relative to each other when you focus or zoom. Tiny motors, often ultrasonic or stepper motors, shift these elements by fractions of a millimeter to bring an image into sharp focus. Right behind the lens sits the aperture mechanism. This is a ring of thin metal blades that slide over each other to form a perfectly circular opening. These blades are engineered with extreme precision because even a slight imperfection would affect how light enters the camera. The aperture isn't just about brightness, it determines how light spreads across the sensor, which is why it influences background blur and sharpness. Next comes the shutter. In traditional cameras, especially DSLRs, this is a physical curtain system made of lightweight but durable materials. It snaps open and closed at incredible speeds, sometimes as fast as 1/8,000th of a second. In mirrorless and smartphone cameras, this is often replaced or supplemented by an electronic shutter, where the sensor itself turns on and off to simulate exposure time. And then we arrive at the most important component, the sensor. A digital sensor is essentially a silicon wafer covered in millions, or even hundreds of millions, of photodiodes. Each photodiode corresponds to a pixel. When light hits these photodiodes, it generates an electrical charge. The stronger the light, the stronger the charge. But here's where it gets even more intricate. Most sensors use something called a Bayer filter, a grid of red, green, and blue filters placed over the pixels. Each pixel only captures one color, and the camera's processor later reconstructs the full color image through a process called demosaicing, which means combining the separate red, green, and blue data from neighboring pixels to create a complete full-color image. That processor, often referred to as the image signal processor, or ISP, is the brain of the camera. It takes raw electrical data from the sensor and transforms it into an image. This includes noise reduction, color correction, sharpening, white balance adjustments, and compression. In smartphones, this step is incredibly advanced, often involving computational photography techniques powered by machine learning. Now, how do all these parts come together physically? Inside a dedicated camera body, like those made by Sony, Canon, or Nikon, everything is mounted onto a rigid internal frame. This frame ensures that the distance between the lens mount and the sensor, called the flange distance, is exact down to micrometers. If that distance is off, your images won't focus correctly. Circuit boards are layered behind the sensor, connecting it to the processor, memory, and power system. Heat management becomes critical here, especially for video. Many cameras include heat sinks or even small internal fans to prevent overheating. Now compare that to smartphones. In an iPhone or Android device, the same principles apply, but everything is compressed into a module smaller than your fingertip. The lens elements are tiny, often plastic instead of glass, and fixed in place. Instead of moving large lens groups, smartphones rely heavily on software to simulate zoom and depth effects. The sensor is smaller, but the processing power is far greater relative to its size. Companies like Apple and Samsung Electronics invest heavily in computational photography, where multiple images are captured in rapid succession and combined into a single final photo. This is how your phone can produce sharp, bright images, even in low light, something early cameras could never do. Now, let's talk about the companies themselves. Nikon began by manufacturing precision optical instruments, microscopes, binoculars, military optics, before becoming a photography giant. Canon started with a goal to build Japan's first high-quality 35mm camera and grew by mastering both optics and imaging technology. Sony entered later, but reshaped the industry by dominating digital sensors and pushing mirrorless cameras into the mainstream. These companies became massive, not just because they sold cameras, but because they controlled entire ecosystems: lenses, sensors, processors, and manufacturing pipelines. Sony, in particular, supplies image sensors to a huge portion of the global market, including competitors and smartphone manufacturers. Now let's talk about something people rarely think about: the actual cost of building a camera versus what it sells for. A modern professional camera body that retails for $2,000 to $4,000 might cost roughly $600 to $1,500 to physically manufacture. The sensor alone can cost anywhere from $100 to $500, depending on size and quality. Precision lens systems, especially professional lenses, can cost hundreds or even thousands to produce due to the glass quality and manufacturing tolerances required. Add to that the processor, materials, assembly, testing, packaging, and logistics. But the biggest hidden cost is research and development. Companies spend billions over time designing sensors, improving autofocus systems, and developing new imaging technologies. When you buy a camera, you're not just paying for the hardware, you're paying for decades of innovation. Historically, the margin between cost and retail has varied. Early film cameras were expensive luxury items with relatively high margins. As production scaled in the late 20th century, costs dropped, and cameras became consumer products. Today, margins on hardware can actually be tighter, especially in competitive markets, because companies rely on lens ecosystems and brand loyalty for long-term profit. Now consider scale. There are billions of cameras in existence today, but most of them are inside smartphones. Estimates suggest that over 90% of all photos taken today come from phones. Dedicated camera shipments, which once reached over 100 million units annually in the early 2010s, have dropped to under 10 million per year as smartphones took over. Financially, the camera industry still generates enormous revenue. Combined imaging divisions from companies like Canon, Sony, and Nikon bring in tens of billions of dollars annually. Canon alone generates billions each year from cameras, lenses, and imaging systems. Sony earns a significant portion of its profits from image sensors used across the entire tech industry. So, even though fewer standalone cameras are sold today, the total camera economy is larger than ever, because every smartphone is now a camera. Now let's shift from still images to motion. A video is not fundamentally different from a photograph. It's just a rapid sequence of images shown one after another. Early motion experiments in the 1800s used spinning discs and sequential images to trick the eye. Eventually, film cameras captured continuous frames on strips of film, creating true motion pictures. The leap from photography to video required solving speed and data problems. Instead of one exposure, cameras needed to capture 24, 30, or 60 frames every second, each one properly exposed and focused. In digital systems, the sensor continuously captures frames, and the processor encodes them into a video stream. But raw video data is enormous, far too large to store efficiently. So cameras compress it using codecs like H.264 or H.265, which reduce file size by storing only changes between frames rather than every pixel every time. And that brings us to storage. Early photography used physical materials: metal plates, film, paper. Today, images are stored as digital files. A JPEG is compressed and processed, designed to be small and easy to share. A RAW file is much larger, preserving nearly all the data captured by the sensor for maximum editing flexibility. Video files go even further. They store not just images, but timing data, audio tracks, compression instructions, and metadata. All of this is written onto solid-state memory, tiny chips capable of holding hundreds of gigabytes or even terabytes of data. What's truly remarkable is how far we've come. From Nicéphore Niépce waiting hours for a single exposure, to capturing 4K and even 8K video at high frame rates on a device that fits in your pocket. From chemical reactions etched onto metal plates to billions of pixels processed instantly. And yet, the foundation hasn't changed. A camera is still just a machine that captures light. Every innovation, every company, every sensor, every lens is just a refinement of that original idea. The complexity you see today isn't because the concept changed. It's because we kept pushing the limits of how precisely, how quickly, how cheaply, and how massively we can capture the world around us.